Good day. My name is Samuel Ayankosho. I'm from the American University in Cairo. My research area is in robotics and control. I'll be presenting the paper titled Modeling and Control of a Double Inverted Pendulum using LQR with Parameter Optimization through GA and PSO. The first author is Dr. Maki Abib. The presentation outline. I will start with the introduction, talking about the applications of inverted pendulum, the modeling methods and control techniques that has been used so far for the system. And for the double inverted pendulum we are going to be considering, we are going to present the model using the Euler-Lagrange approach, then to the control design, which includes control goals and requirements. And we designed controllers such as pole placement controller, LQR controller, and we tuned the parameters of LQR using GA and PSO. We also present the simulation results, and we are going to discuss the results. And the last is conclusion. The introduction now. An inverted pendulum system has a wide range of applications. Its operational principle is used in rocket and missiles launch, Segway design. We are showing that through this figure. The system is nonlinear, unstable, multivariable, and undertreated. And it can be modeled and controlled in state-space domain. The two main modeling techniques are done through Euler-Lagrange dynamic formulation and Newtonian dynamic formulation. And the control methods that are applied to the linearized equations of single and double inverted pendulum include PID control, pole placement control, linear quadratic regulator control, fuzzy control, model predictive control, SMC, and in some cases, they combine two of these control techniques to form hybrid control, such as PID and fuzzy with sliding mode control, and so on. Our paper focuses on the modeling of a double inverted pendulum using Euler-Lagrange formulation. And we also consider the analysis and comparison of a linearized double inverted pendulum system with two different control techniques, pole placement and LQR method. And we validate our result through simulations, and GA and PSO were also used to tune the Q and R matrices used in the design of LQR controller. The modeling of double inverted pendulum. This is the Euler-Lagrange dynamic formulation, where L is the Lagrangian, T is the total kinetic energy, and P is the potential energy. What we do in modeling the system is to find L, and it's by getting T and subtracting P from T. So after getting L is substituted into this Euler-Lagrange dynamic formulation, and we're going to get three equations based on the system variables, the S0, θ1, and θ2. So these three nonlinear equations are then linearized about the system equilibrium point at θ1 equals 0 and θ2 equals 0. And the following conditions were hold at the equilibrium position. Cosine of θ1 will be equal to 1, sine of θ1 will be equal to θ1, cosine of θ1 minus θ2 will be equal to 1, and so on. And the resulting linear equations are these. These linear equations are then represented in state space form. And this is our A matrix. This is the B matrix. Our C is an identity matrix, and D is 0. The size of C is 6 by 6. And these are the parameters we used for our system. For the control design, starting with the control goals, our desire is to stabilize the lower and upper pendulum at upright position, and we want to command the car to a new position, 0.1 meters. For the pendulums now, the requirement is for the pendulums to settle at less than 3 seconds, while they have a maximum overshoot, which is not more than 20 degrees. Also for the cat, we want the settling time to be less than 3 seconds and the rise time to be 0.5 seconds. I mean, less than 0.5 seconds. So we design pole placement controller here. In the design of pole placement control, the closed loop poles are located at desired position, but a necessary condition for placing a pole at an arbitrary point is that the system must be completely state controllable. This test is also known as the Kalman's test. So based on the requirements I mentioned in the previous slide, we set our dominant pole to have 4.6% overshoot and 1 second settling time, and a separation factor of 2 was used for the other poles. To our LQR control design, LQR is an optimal control technique. It accounts for Q and R matrices, which is representing the weight or the cost functions of the state deviation and the control input respectively. The objective in LQR is to get an optimal gain value or optimal controller that minimizes this performance index. And this is the block structure for pole placement or LQR controller. These are the gain for state, the second state to the sixth state, and this is the gain for the fourth state. Also, we tune the parameters of LQR using GA and PSO. In tuning the parameters, we define an objective function which is based on the control input and integral time square error. This is the flow chart of GA and PSO algorithm. For the GA, we start with the initialization of the genes, and we initialize other GA parameters like population. We set it to be 100. Then we evaluate the fitness function of each chromosomes. We then select the fittest of the population and do operations such as crossover and mutation. We then check here if the stopping criteria is met. The stopping criteria could be the number of generations or iterations, the time limit, the function tolerance. So if any of this is met, we output the optimal solution. If not, the generation will be increased and the process will continue. PSO is almost similar to GA. So after evaluating the fitness, we are going to calculate and update the personal best of each particle and the global best of the population. Then we are calculating and updating the position and velocity of the particles here. We check again for the stopping criteria. If it's met, we output the optimal solution, which is the global best particle. If not, we increase the iteration by 1. So this is the block diagram we use in implementing the GA or PSO tuning. For a simulation result now, This is the desired pole locations we got. And this table is showing the summary of the system performance with pole placement control. The rise time, the settling time, the peak amplitude, and the steady state error of the CAT, the lower pendulum angle, the upper pendulum angle are shown here. The CAT settled at 1.6 seconds. The lower pendulum is settling at around 1.5, while the upper pendulum around 1.7 seconds. This is the result of pole placement control. For the LQR, we did manual tuning and we consider first 4 cases. For the first case, Q has the diagonal elements all equal 1 and R is 1 as well. So this is the result of the CAT and the pendulums. The settling time of the CAT was around 4.9 seconds, while the lower pendulum around 3.45 seconds. And for the second case now, we increase the first element in Q to be 10,000 and the results improved. The CAT settling time, for instance, improved from 4.9 to 1.59. And here we look at if we reduce R, what will be the effect on the performance of the system too. And as shown here, the settling time is also improving. And at the same time, the rise time of the system is also improving. Then this is showing the plot of the fourth case. This is the control effort. We have the effort to be around 100 here, and we have the CAT response there, and the pendulum response is at the middle. For the simulation results, the simulation result of GA and PSO tuned LQR. This is the Q and R we got by the through genetic algorithm, and this is the Q and R we got through particle swarm optimization. We did both optimization in MATLAB using the GA and PSO toolbox, and these are the parameters we set: initial population as this, the maximum iterations or generation as 3. This is our lower bound and this is our upper bound. And from these results, the settling time in particular, could see here that the settling time of the CAT improved with PSO algorithm. And at the same time, for the lower pendulum at 2 and for the upper pendulum 2, the settling time is improving. Here, I'm going to show a short animation we did when we desired the CAT to be at 1 meters. So this is the response of the system. This is showing how the system would behave. So to the discussion of our results now. From the simulation result, the PSO tuned LQR gave the best transient performance in comparison with the GA tuned and manually tuned LQR and the pole placement controller. The settling time of the CAT and the lower pendulum and the upper pendulum were improved by 11.85%, 51.26%, and 39.9% respectively by the PSO tuned LQR when compared with the result of the pole placement controller. In addition, we find out that the PSO tuned LQR gave a better result than the GA tuned So PSO is better than GA when searching for the optimal values of the Q and R parameters used in the LQR control. Conclusion, the control goals and requirements were met by the controllers. The pendulum stabilized in less than 3 seconds, the cards also, and the rise time of the cards was not exceeded, the rise time we set. And furthermore, the PSO tuned LQR gave the overall best transient performance in comparison with GA tuned and manually tuned LQR and the pole placement controller. In the future, uh, in the future, our research will be centered in the development of a modular and cheap double inverted pendulum. And our work will include the intelligent and robust control of the system. Thank you so much.